Good day everybody. In this class I shall be discussing about two important logic circuit categories known as registers and counters. As the names indicate, registers register binary data within the circuit, and the counters count the number of voltage pulses that are input to the system and gives us a binary output, which is the count of the number of pulses that are input to the system. So these systems are applied in various application areas. Like in computers, we find the registers and counters extensively used in computer systems. So these are used in instrumentation. So many instruments where we obtain the display in digital form use registers as well as counters. Similarly, communication systems wherein we have digital communications as the modern means of communication today, and these digital communications use most of the time binary data or uses the signal in binary form, and these signals are to be handled by digital circuits, and therefore in the digital circuits we use registers and counters and in the various subsystems of a communication system. Similarly, other electronic gadgets like the digital clocks use counters as well as registers in them. Other areas include control systems and other digital processing areas where we deal with digital signals and data, use registers and counters for various applications. In the last class, we studied about flip-flops. These registers and counters use flip-flops as their building blocks. First, I shall take up a register circuit known as a shift register. So let us see how a shift register works. In a shift register, we use several flip-flops, either D flip-flops or SR flip-flops or JK flip-flops, which we discussed in the last class. So in a 4-bit shift register, for instance, we use, I'll take another shade. For instance, in a 4-bit shift register, we use 4 flip-flops, and in general, in an n-bit shift register, we use n flip-flops. So let us say, so these are the flip-flops, 4 flip-flops. Let me call it as F4, this one as F3, F2 and F1. Now these flip-flops can be D flip-flops or SR flip-flops or JK flip-flops. Let me take the diagram of an SR flip-flop as an example. Let me take an SR flip-flop, and using SR flip-flops we can get a D flip-flop by inverting the S input and applying it to the R input. Now this is our input, overall input, wherein it is called serial input, through which we can feed digital data, binary data into the shift register. Then the Q bar outputs are directly connected to the J and K inputs respectively if it is a JK flip-flop, or the S and R inputs if it is an SR flip-flop. Similarly, so the Q and Q bar of the next flip-flop are also connected to the subsequent inputs, SR inputs of the subsequent flip-flops. And here we have the final output. If we call it as Q1, so this will be Q2, this will be Q3 and Q4. Now all these flip-flops have clear inputs. So by applying the clear signal here, we can clear the flip-flops to start with, in which case all these flip-flops attain 0 state. That means this Q1, Q2, Q3 and Q4 will be zeros once the clear input is applied. Then we apply the clock to it. So let us say this is the clock. To all the flip-flops. This is CK, the clock input of each of these flip-flops. Now let us examine the circuit, the function of the circuit. Now initially, if it is cleared, all these outputs, the flip-flop outputs will be zeros, and if we apply a serial input, like a serial binary input, let us for instance take the data of like serial input like 1 1 0, say 1 0. Means first we apply one level and then apply a clock, then apply the second one, apply the clock, the next the 0 is applied and the clock is applied, the next 1 is applied and the clock pulse is applied, and finally 0 is applied and the clock is applied. So in this, when this is done, let us see what happens to the circuit. And as I mentioned earlier, the clock waveform is a pulsed waveform, so like this. If it is a TTL shift register, you have to apply TTL high and low levels in order to get a good response from the circuit. Now, if this is the first clock pulse, and let us assume that the shift registers respond to the falling edge of the clock pulses, so then we can examine how the system works. We can also explain it by taking that the system works during the rising edge also. So let us consider, I change the nature, and let us assume that the system works during the rising edge of these pulses. The flip-flop responds during the rising edge of the pulses. Now, during this period, first period, if 1 is applied to the data, then S will be 1 and R will be 0 because it is connected through a NOT gate. And until the clock pulse is applied, output doesn't get disturbed. Now when this 1 is applied here, and obviously 0 there, and when this clock transition occurs from 0 to 1, so that time the Q out of this flip-flop, Q output of the flip-flop will be set to 1, or this 1 is transferred to Q, and obviously Q bar will be 0. Therefore at this instance, so Q will be a 1, at this instant, at this instance. Then initially, let us see what is happening with the other flip-flops. Before the clock pulse is applied, so this was a 0 and this was a 1 because it was cleared earlier, and because it is 1 and this is 0 and 1, so when the clock pulse occurs, it will be 0 and 1. And here also it was a 0 and 1 because it was initially cleared, and this 0 and 1 now when the clock pulse occurs will be transferred here and it will be 0 and 1, and this 0 and 1 which was here will be sent to the will be passed to the output. Therefore, all of them remain 0 zeros initially. So initially this was also a 0 and later on it becomes a 1 when this clock pulse is occurred because this one shifts to this. So at this time, during this time period, this is a 1 and all others are zeros. Now when the next clock pulse occurs, that means during the third instance, because this is already 1, S is 1 and R is 0, when the third clock pulse, when the second clock pulse comes, so this output will be a 1. Therefore, this one will be transferred to this one. So it will be a 1 here, and initially when the second pulse occurs, initially it was 0, therefore this 0 will be shifted to this, and the third output will be 0 after the second clock pulse. Similarly, it was a 0 here, and when this second clock pulse occurs due to this 0, so during the third pulse this output also becomes 0. Now what happens to this? First it was a 1. When the first clock pulse occurs, this was a 1 and therefore this got transferred to 1, and during the second instance, second clock pulse time, this remains as a 1. Now when the second clock pulse occurs, of course, after this 1, during the first clock pulse it remained as a 1, and during the second clock pulse we are supplying an input of again another 1. So during the second clock pulse, since the input is a 1, so this 1 gets transferred here and therefore it will be a 1. And during this input, during this period, so this one remains a 1. Now the third input, that means during the third input, so it is a 0 now. Therefore, when the third clock pulse comes, and during this period, since it is a 0 here during this period, when this clock pulse comes, so this 0 gets transferred to this, and this one gets transferred to this, and this one gets transferred, and so on. So this 0 got transferred here, and this 0 will get transferred in the next instance, and this one gets transferred during this instance, and the first one gets transferred now during the fourth clock pulse duration. Now after 0, 1 comes here, and then this 1 goes here, and this 0 now, this 1 after another clock pulse, during this 0 now goes to this, and this 1 has already gone through this, and during the next clock pulse this 0 goes to this, and the second one goes to this, and this one goes to this place, and this 0 goes here when this is 0. So this is how the data gets shifted from the left side to the right side. So if you take a snapshot at any time, say after the second clock pulse, rather after the first clock pulse, the first bit goes here, and after the second clock pulse, so this will reach this point, and after the third clock pulse it will reach this point, and after the fourth clock pulse it will reach this point. And whatever is the serial data, it gets shifted like this. I just now talked about the first bit. Similarly, the second bit also follows. Hence, the first bit which goes after one clock pulse here will go after 4 clock pulses to this place. There is a 0 missing. After 4 clock pulses it reaches this output point. Hence, its name is a shift register. So we can feed in a serial binary data like high voltage and low voltage and combinations of that at the input, and this gets shifted to into the shift register. Now, this shift register can be used as a serial in and parallel out register. Let us see how it works as a serial in parallel out register. A serial in parallel out register is one wherein you can send data serially. It is a register which has a serial input. It also has a clock which goes to all flip-flops inside, as we have seen in the previous sheet. So this is the clock. So it also takes a clear input, as we have already seen, and what comes out is so these outputs, namely Q4, Q3, Q2 and Q1. In fact, in practice these are given in the reverse order, and this is Q0, this is Q1, Q2 and Q3. It starts from 0. The first flip-flop output is Q0, second flip-flop output is Q1, third flip-flop output is Q2, and the last flip-flop output is Q3. That means here, so these Q outputs are taken out. This is Q0, this is Q1, Q2 and Q3. So the first flip-flop output is Q0 and the last flip-flop output is Q3. It has a clear and clock inputs. Now, when we feed data of this type, so this data goes into it and they appear here. After 4 clock pulses, so this bit or this input will go to this location, and this input will go to this location, and this 0 goes to this location, and this 1 goes to this location. If it is a 4-bit shift register, after 4 clock pulses, so the first 4 serial in data goes to the respective flip-flop outputs as shown here. Now, using an external circuit, you can read this parallel output. You can sense at a particular time instant, single time instant, or after the 4th clock pulse is applied, during the next clock pulse instance, you can sample this. If you sample this, you will get this one, and if you sample this, you will get 1. If you sample this, you will get 0, and if you sample this, you will get 1. That means what? The 4-bit information that is applied serially into the flip register are available parallelly at the parallel output. So these are parallel outputs, and this shift register can be used as a serial in and parallel out register. So we can feed in serial data, and we can make use of it in a single instance. We can make use of the parallel data in a single instance. Similarly, it can be used for serial in and serial out application also. Once you send the data serially, within 4 clock pulses, a 4-bit data gets into the register at certain frequency, and then if you change the clock rate, and if you want to output these 4 bits in a different rate, at a faster rate, then you can change the clock rate and you can get it at a faster rate. So serial in and serial out application also can be, this can be used for serial in, serial output application also. In such applications, typically we use a different rate for input and another rate for the output. Then it can also be used as a parallel in and serial out shift register. So what it means is, we can store data into the shift register parallelly, and by means of clock pulse application we can get this data sequentially. Suppose 1101 is applied to the register parallelly, it is entered into the register, and then with clock pulses, if you want this output to be available sequentially, 1 bit after another sequentially in the same order, this can be used. Then the question is, how do we store this information? How do we load this parallel data into the shift register? So let us look back at the shift register circuit. Now we have to load data into the shift register with parallel inputs, through parallel inputs. It can be done with the help of the preset input. Suppose this is the preset input for every flip-flop. So this is the preset input. Now in some shift registers, it can be sensitive to the low level here. The moment a low input appears here, irrespective of whatever is, irrespective of the inputs and irrespective of the clock pulses, the moment the preset is a 0, output will be 1 for the flip-flop. That means the preset input and the clear inputs, as I mentioned earlier, the preset input and the clear inputs override these inputs, the SR inputs. Hence, irrespective of the conditions at the input, the moment a 0 appears here, this becomes a 1. In some flip-flops, it is sensitive to 1. When the preset input is a 1, the output will be 1. But usually in the SR flip-flops, it is sensitive to logic level 0. Now, an AND gate can be used as a control circuit. We can feed in different data to the preset inputs by external means, and this data entry can be controlled with the help of a preset control input like this. And please note that when this input is a 0, this is the preset input. When the preset input is a 0, if this is a 0 here, irrespective of this, at the AND gate output it is a 0, at the NAND gate output it is a 1. Therefore, all the preset inputs will be 1 if this preset is a 0. That means whatever are the inputs you are applying to the presets through these inputs, these blue lines, cannot affect the flip-flops, because the flip-flops are presetted only when this PR is a 0. Now this, if you make this PR 1 by making this preset input 0 irrespective of other inputs, so this preset is non-effective because it is a 1 when preset is 0. That means when 0 is applied to this preset line, you cannot apply any input and you cannot disturb the preset input through these inputs. On the other hand, when preset is made to be a 1, and at that instant, if this is also a 1, with both inputs as 1, this becomes 1 and the NAND gate output becomes 0 and the flip-flop gets preset to 0. Therefore, the flip-flop gets preset to 1. Hence, if there is a 1 applied here, this 1 gets loaded into the flip-flop if preset is a 1. On the other hand, if preset is a 0, this 1 cannot get loaded in because preset input is a 1. If the preset input is a 1, this cannot get set. Therefore, these inputs which can be used for loading the data into the shift register, say this is Q0, this is Q1 input, Q2 input and Q3 input. So these inputs get loaded to the respective Qs if preset is a 1. If preset is a 0, so whatever inputs you apply, they cannot get loaded into the shift register. Hence, this shift register can be used to load parallel data into the shift register through this preset input and through these inputs. And once the data gets loaded, for instance, let me take a data set like same 1101. Then upon making the preset equal to 1, this gets loaded. So this one will become 1, this one will become 1, and when this is 0, however, this PR will be 1 and this will be a 0 itself if it is previously if all are cleared. Okay, and when this 1 is applied and preset is 1, this one will become a 1. Therefore, this data 1101 gets loaded. This data 1101 gets loaded to this place 1101. And once these are loaded, you make the preset again back to 0, bring it back to 0. After making it, initially if it is 1, make it 1 for some duration and then this gets loaded and then make it 0. Then these inputs will be ineffective. Then you apply clock pulses. When you apply the first clock pulse, so this one which appeared here will get shifted into this. So this 0 which got loaded here will shift into this, and this 1 which was loaded here will shift into this after the first clock pulse. Now after the second clock pulse, whatever was there here will be transferred here, whatever there was here will be transferred here, and so on. And therefore, whatever is the serial data that is loaded into this, that data gets shifted out serially. Serial out. Therefore, it can be used for parallel in and serial out purposes also. There are many other variations of these possible using the shift registers. There are other important building blocks, and the class is known as counters, as I have already mentioned. And as the name indicates, the counters count the pulses. So if you have a counter and you feed in pulses here, like clock pulses, the counter counts these pulses and it gives us the binary equivalent of the count. If 4 pulses are applied, it will give you a binary equivalent of 4. That means it will be 0, 1, 0, 0. After the 5th clock pulse is applied, the count becomes 1, 0, 1, 0, 1, 0, 1. For instance, after the 8th clock pulse, it becomes 1, 0, 0, 0. So this gives a binary number corresponding to the counter. So this type of counter is known as a binary counter. There are other types of counters which can count in a required fashion. If you want, for the first 2 pulses, if you want 1 and 2 respectively, and for the 3rd pulse, if you want 5 to be output, you can make the counter to behave like that. Whereas in the binary counter, it counts the number of pulses and gives the binary output corresponding to that. So this is what is known as a counter. So the counter has binary outputs, and it has the clock input. In fact, it counts the clock pulses, as I already mentioned. There is a clear input to clear the counter and to make it all zeros. So there is a clear input also. Now let us see how we can make a counter using flip-flops. As I mentioned, there are different kinds of counters available, and let us see one category of counters known as ripple counters. As the name indicates, so this counter counts the number of pulses and the output goes as like a ripple. That's why the name ripple counter. Let us take a 3 flip-flop counter. And let us take toggling flip-flops. Let me recall that a toggling flip-flop works like this. It has a T input and it has Q bar outputs, because it has a clear input also. Now, when you give a 0 to the toggle input, and if it is initially cleared, 0, when you give a 0 input, it does no response occurs. And if you make it a 1, that means initially it is a 0 and you make it a 1. So it doesn't respond. But when you make it from 1 to 0, make a transition from 1 to 0, then this flip-flop toggles from 0 to 1 state. And when you make it again 1, it doesn't respond. But when you make again the next transition from 1 to 0, so it will get toggled from 1 to 0. So this is what happens when the T flip-flop is negative edge sensitive. That means when the toggling input, for every negative transition at the toggling input, the output toggles. So when you apply this kind of input to the T input, if this is the T input, what happens to the Q? If Q is initially 0, it remains for this 0, it remains a 0 because there is no negative transition there. And when the next pulse 1 occurs, still there is no negative transition, therefore still it will remain 0, output will remain 0. Now, during this negative transition between 1 and 0 here, the flip-flop toggles to a 1 state. So it toggles to a 1 state here. and it continues to be in that state. And when the next clock transition, where the transition occurs at the toggle input, from 0 to 1, no change takes place, therefore it continues to remain in a 1 state. Now during this negative edge transition at the toggling input, the output toggles, therefore it toggles back to 0 level here. Now during this 2 pulse inputs, it remains there at 0 level itself, and only during the next negative transition it becomes a 1. So this is how the toggling flip-flop works. And for a square wave input like this, so its output is like this. And please note that if its frequency is such that it is 1 kilohertz, that means the 1 and a 0 occurs within 1 millisecond. Then so this one also gives a square wave output. At this point it gives a square wave output, but the output here is half of this frequency. That means this toggling flip-flop is dividing the frequency of the input square wave by 2, and it is giving an output square wave. Hence a toggling flip-flop can be used as divided by 2 counter. It's a divided by 2 circuit. It can act as a dividing circuit for the frequency. If it is 1 kilohertz at its input, and it will be 2 kilohertz at its output. So that's because only the toggling flip-flops responds only to the negative transitions. Now if you apply this Q output to another toggling flip-flop, please note that this T flip-flop responds to again negative transitions here. That means it responds to the negative transitions over here. If it is initially cleared, it would be a 0, and to this transition this second flip-flop responds, therefore it toggles to state 1 and it remains in the same state until this next negative transition occurs. So due to which it will again toggle from 1 to 0 and so on. Hence the frequency gets divided further by 2, and if you have another flip-flop there, so it will further get divided by 2, and that's how it can work like a dividing counter. And the same thing I'm showing it here with 3 flip-flops, and here this is the toggling input, overall toggling input of the first flip-flop. So this is the input, and this Q is applied to the toggling, Q output is applied to the toggling input of the second flip-flop, and similarly this Q output is applied to the toggling flip-flop of the toggling input of the next flip-flop. And if you want more counts, you can apply more number of flip-flops and do the same thing. Now let us see how this is counting. Please note that when the first pulse goes in, we have the output remaining as 0, 0, 0 here for the first pulse. Only when the second pulse goes, this is becoming a 1, and because there is only a positive transition here, it will remain 0, and because there is no transition here, this toggling flip-flop doesn't respond, therefore it will remain as a 0. Next, when the third pulse goes into the flip-flop, this one remains a 1, and so this flip-flop remains the same, and it would go like this. for the third pulse. Well, let me not talk in terms of pulses. If I talk this as a 0 and 1 combination as one cycle of the input, for the first cycle, after the first cycle, its output will become a 1. And for the second cycle, after the end of the second cycle, it will become a 0. And during the third cycle, it remains as a 0, and at the end of the third cycle, it will become a 1. So if I talk in terms of number of cycles, after the first cycle, so this one will be a 1. This one will be a 1. After the second cycle, so this one becomes a 0. And after the third cycle, this one will be 1. And fourth cycle, this one will be 0, and so on. Because, so it works like this. After the first, it will become 1. After the second, it will become 0. After the third, it will become 1, and so on. Now, we have the same situation over here. Again, initially it was, say, 0, 0, 0. All was, everything is cleared. Now, after the first cycle that is applied to this one will be a 1. And this is after the end of the next cycle for this flip-flop input, after the end of the next cycle, that means at this point, this one will be a 0, like what I have given here. For the second flip-flop, after the end of the first cycle at the input, this one will change to 1. Now after the end of the second cycle, this will go back to 0. So please note that as one cycle here is equal to 2 cycles of the input waveform. Therefore, the count will progress like this. Initially it is 0, 0. So it is becoming 1 and a 0. And during this instant it is becoming a 0, and this is a 1. And this instant it is becoming a 1, and this is a 0. And this is becoming 0 and 0 again. Now if you have another stage at the output, then it will respond to this negative transitions. So it will remain 0 here, it will become a 1 for this instant, it will become a 0 like this. That's how we got the frequency division. But if you look at the binary outputs, you will find that initially it is a 0, 0, 0, 0, 0, 0. So this is a 0, 0, 1, this is 0, 1, 0, this is 0, 1, 1, this is 1, 0, 0. And so here, if I complete the rest, so this will be a 1, 0, 1, then 1, 1, 0, and it goes on like this. Therefore, for different pulses, you get the binary output here. So it will be all zeros, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0. For 5, you will get 1, 0, 1, and so on. Therefore, the binary counter outputs, when you take the binary counter output, sample them, so these outputs give you the count of the pulses. Hence, it acts like a counter. It can count the input cycles. On the other hand, it works like a frequency divider also. So this is known as a counter. It can count up to 8 pulses, and for 8 again, all of them will become 0, 0, 0. If you have another flip-flop here, so its output would be 1. So if you have 3 flip-flops, it can count up to 8 pulses. If you have 4 flip-flops, it will count up to 16 pulses, and so on. So such counters are known as ripple counters, because whatever is the input, it goes to the output with the timing as given in the previous sheet, and it goes in a ripple as a ripple, the outputs go as ripple, therefore its name is called a ripple counter. Now, if you want to terminate the count at 5 itself, say, it counts from 0 to say 7, that means 8 states, and counts back. And now if you want to terminate it at 5 itself, that means you should sense a situation where it is a 101. And the moment 101 occurs, if you clear, that means you take it through a NOT gate and you take it as it is, so these inputs, and apply it through an AND gate. Please note that the AND gate will give a 1 when there is only 101 at its input. So when there are 101 here, there will be 111 here, output will be 1. And you give it to the clear inputs of the T flip-flops, and it will get cleared to the moment this comes instantaneously within a very short time, within a few nanoseconds, it will get reset to 000. And it will start counting again 001, 010, etc. up to 100, and for a very short time it will be 101 and it gets reset to 0. So such counters are known as modulo 5 counters. Similarly, you have counters with other modulo operations, and you have, other than ripple counters, other than this category, you have synchronous counters also available. And these counters are used extensively in computers and other electronic circuits which handle digital data.